robots are a well-established solution for environmental surveying, exploration, and inspection, thanks to their superior maneuverability and agility. Nowadays, the algorithms that provide these capabilities rely on GNSS and vision, which are obstructed in some environments of interest, for example, indoors and underground, or in the presence of smoke and dust. In these environments that inhibit the sense of sight, nature provides an alternative solution that instead relies on the sense of touch, embodied in the morphology of animals. By feeling the environment surrounding the agent, it becomes capable of navigating safely using tactile cues. In this work, we propose an approach that allows a quadrotor to navigate using tactile information from the environment. We endow a conventional quadrotor with a novel robotic finger design that embodies compliance and sensing capabilities, which enables it to safely establish and sense contact. The robotic finger takes on an under-actuated design comprising rigid links connected via stiff revolute joints, all actuated by one tendon. Joint encoders measure the joint angles and give the system the capability to estimate contact forces from the joint angle displacement. The planner then uses the contact force to generate new pose references that align the system with the environment and move it along. All the while, the system ensures that it maintains contact, preserving the basis for a new reference. The system successfully performs environment following in a total of 36 successful flight experiments. It handles angular offsets of the environment of more than 20 degrees and surfaces that combine multiple relative orientations. The system can also support superimposed altitude tasks throughout the tactile navigation procedure while navigating along a wall. Our approach paves the way towards blind navigation in GPS-denied environments or in situations where the conditions inhibit the sense of sight. When used in conjunction with vision-based control approaches, tactile-based navigation can aid drones' autonomy in realizing search and rescue tasks or underground exploration missions. Future work will look into improving tactile-based autonomy by mapping the exerted force at the end-effector to low-level attitude commands, completely removing the need for external position measurements. New contributions to the design of multiple active limbs will enhance the richness of tactile sensory feedback in various directions for aerial navigation. They will also extend the range of possible manipulation tasks drones can accomplish, including navigating in vision-denied environments using tactile cues to grasp and carry an object of interest.